Hello everyone, hope you are doing well. I am Abhinav and welcome to my YouTube channel. In this video, we will discuss about PAL or Programmable Array Logic. PAL is the most commonly used programmable logic device. So, in this video, we will discuss what are the programmable logic devices and their types and how to solve the problems using programmable logic devices and their advantages, their limitations and their applications. Let us know what are the types of PLDs. PLDs have two types of arrays, namely AND array and OR array. Based on this, we have three types of PLDs. First one is programmable read-only memory, or we can call it as PROM. In this, AND array is fixed and OR array is programmable. Second one is PAL, which we are going to discuss in the video. It has a programmable AND array and a fixed OR array. Third one is programmable logic array or PLA. In this, both AND array and OR array are programmable. Let us know what is PAL. PAL is the most commonly used type of PLD, which has programmable AND array and a fixed OR array. In this, OR array is fixed, so it's not flexible compared to PLA. PAL consists of small PROM and additional output logic to implement a particular desired logic function, or we can call it as combinational logic. It's the representation of PAL. Now we can see it consists of n inputs going through programmable AND array and then the fixed OR array and comes out as m number of outputs. Let us discuss how to solve problems using PAL. We use PAL to solve sum of product problems or SOPs. Let's consider the first problem. In this problem, we can see the function f0 of ABC is equal to m0, m1, m4 and m6. f1 of ABC is m2, m3, m4, m6 and m7. f2 of ABC is m0, m1, m2 and m6. f3 of ABC is m2, m3, m5, m6 and m7. So we will simplify this using K-maps. Let's consider f0. In this m0, m1, m4 and m6, we put 1 in these cell values and we'll group this as pairs. And the function will come out as f0 is equal to a complement b complement plus a into c complement. Let's consider f1. In f1, the cell values at 2, 3, 4, 6 and 7 is 1. So in 2 it's 3, in 6, 7 it's 6 and 4 it's 1. So these 4 ones we can group this as acquired, and this one and this one we'll group this as a pair. So f1 is this squared gives the output as b, and this pair gives the output plus a into c complement. So f1 is b plus a into c complement. Then f2, in f2 0, 1, 2, 6 we have 1. So 0, 1, 2 and 6. In this position we put the cell values as 1. So we will group this one and this one as pair, and this one and this one as pair. This gives a complement b complement as output, and this group gives b into c complement as output. So f2 is a complement b complement plus b into c complement. And in f3, in the cell values at 2, 3, 5, 6 and 7 are 1. So in 3 it's 1, in 2 it's 1, in 7 it's 1, in 6 it's 1, in 5 it's 1. So we can group these 4 as a quad and these two ones as a pair. So f3 is b plus ac. For further simplification, we use product table. Product table contains terms and inputs and output functions. Terms are nothing but the logic functions we solved in the previous slide, like a complement, b complement, b complement, c complement, a complement, b complement, ac complement, B AC. First term is A complement B complement. So the value of A is 0, B is 0. We don't have C terms, so we put a dash in place of C. And second term is A into C complement. A is 1, no B, so we put dash, and C is 0. So first function is F naught. F naught is A complement B complement plus A into C complement. Let's consider second function. We have B, so we don't have A terms, so we put a dash. We have B, so in place of B we put 1. For C we put a dash. Second term is A into C complement, so in place of A we put 1, no B terms, so we put dash. It's C complement, so in place of C we put 0. So F1 is B plus A into C complement. Third function is A complement B complement plus B into C complement. So first term is A complement to B complement. In place of A we use 0, B is 0, and we don't have C, so it's dash. And B C complement, A is dash, in place of B we put 1, and C we put 0. F2 is A complement B complement plus B into C complement. And fourth function is F3 is equal to AC plus B. AC in place of A it's 1, B it's dash, and C it's 1. And for B in place of A it's dash, B it's 1, and in place of C we put dash. So F3 is AC plus B. So let us know how to solve using circuits. Let us discuss how to solve these functions using circuit. We have three inputs, which is A, B, and C, and their complements. And this is AND array, and this is OR array. Let's represent input for programmable array or AND array by cross mark, and for OR array or fixed array by dot. We use separate AND gate for each terms. First term is A complement to B complement, so cross mark it A complement and B complement, and connect it to AND gate. So the output is A complement to B complement. Second term is A into C complement. So we made connections at A and C complement. So the second term is A into C complement. Third term is only B, so we make connections for B. So the term is B. The fourth term is B into C complement. So we make connections at B and C complement and pass it through AND gate. So the output is B into C complement. And the fourth term is A into C. So we make connections at A and C, and we connect it to AND gate. So the output is A into C. The first function is F naught. F naught is A complement into B complement plus A into C complement. So we make connections for OR at A complement into B complement and A into C complement and pass it through OR gate. So F naught, we get F naught, which is A complement into B complement plus A into C complement. The second function is F1, which is B plus A into C complement. So we make connections at B as well as A into C complement and pass it through OR gate. So we get F1. And the third function is F2, which is A complement into B complement plus B into C complement. So we make connections at A complement into B complement and B into C complement by using dot. And the fourth function is F3, which is B plus A into C. So we put a dot at B and we put a dot at A and C. In this way, we solve problems. Let's consider another problem. We have already solved this using K-map. So the first solution is W of ABCD is equal to A complement into B complement into D complement plus A complement BC plus A into C complement. Second function is X of ABCD is equal to A complement B complement D complement plus A complement BC plus AC complement plus BCD complement. Third function is y of abcd is equal to a complement b complement c plus b complement c d complement plus a into c complement. Fourth function is z of abcd is equal to a complement b complement d plus b complement c complement d plus b into d complement. So let's consider all the terms. First term is a complement b complement d complement. Second is a complement bc, and third term is a into c complement. Let's represent in AND inputs. For the first term, it's A is 0, B is 0, we don't have C, and at the D we have 0. The second term is A complement BC, so at A it's 0, at B it is 1, at C it is 1, and we don't have D term, so we put a dash. And the third term is A into C complement, so at A we put 1, we don't have B term, and at C we put 0, and we don't have B term. So the output function is W is equal to A complement B complement D complement plus A complement BC plus A into C complement. And the second function is X of ABCD is equal to A complement B complement D complement plus A complement BC plus AC complement plus BC into D complement. We can notice that the second function is W plus BC into D complement. W is A complement B complement D complement plus A complement BC plus A into C complement. We have same terms. So first three terms are same. We just have BCD complement as another term. So we represent. So we consider another AND input which is W. So we don't have A, B, C, D terms. So we put a dash, and the W we put 1. And BCD complement at B and at C we put 1, at D it's 0, and we don't have W terms, so we put dash. To match this with three terms, we use another 0. So X is W plus BCD complement plus 0. Third term is A complement B complement C plus B complement C D complement plus A into C complement. A complement B complement C is at A it's 0, at B it is 0, at C it is 1, at D and W it is dash. B complement C D complement is at A it's dash, at B it is 0, at C it is 1, and at D it's 0, and at W it's dash. A is AC complement at A it's 1, at C it's 0, and remaining all are dash. So we can notice Y is equal to A complement B complement C plus B complement C D complement plus A into C complement. And the Z is A complement B complement D, B complement C complement D plus B into D complement. In the same way as the previous terms, we use at A it's 0, at B it's 0, and at D it is 1, and C and W it's dash. B complement C complement D is at B it is 0, at C it is 0, and at D it is 1, at A and W we put dash. And for B into D complement, at A we put dash, at B we put 1, and at D we put 0, and for C and W we put dash. So we give up to Z term. Let us understand this problem using circuits. We have 4 inputs A, B, C, D, and this is AND array, this is OR array. First term is A complement B complement to D complement. So we connected A complement B complement D complement to AND gate, and we got the output. Same for A complement B C. We connected A complement B and C and passed it through AND gate, and we got the output. First, in the similar way, we connect it for all the terms. We have first function as W. W is A complement B complement D complement plus A complement BC plus A into C complement. So we connected it to OR gate through dots, and we got the output W. We can notice that the function X is W plus BC into D complement. Rest all functions have 3 terms as outputs, but this X has only 2 terms as output. So we consider another empty AND gate here to match the 3 term output. So we connected this W as an input for X and B C D complement and plus 0, that is this empty AND gate. Similarly, Y is a complement into BC plus B complement C D complement plus A into C complement. We connected to OR gate and got the output Y. And for Z, it is A complement into B complement into D, B complement C complement D, B into D complement. We connected it through dot and passed it through OR gate and we got the output Z. Let's know what are the advantages of PAL. PAL is highly efficient. It has low production cost compared to PLA because PL has AND array and OR array. Both are programmable in PLA, but in PAL we have only AND arrays programmable, OR arrays fixed here. Power requirement is less, and it's highly reliable, and designing is simple. What are the limitations of PAL? PAL is not flexible compared to PLA because PLA has both AND array and OR array as programmable, but PAL has only AND array as programmable. PAL's main limitation is number of AND gates because we have to use separate AND gates for each term. If the terms are more, the AND gates required are also more, so the chances of delay is high. What are the application of PAL? It's mainly used in the solving sum of product or SOP problems. So it is used in combinational logic circuits. Uh, the examples are decoders, state machine, and counters. Let us know how PAL can be used in decoder. Decoder is an electronic component which receives n number of inputs and gives 2 power n number of outputs. We can see the logic diagram of decoder here. It's the internal diagram of 3:8 decoder which receives 3 inputs and gives 8 outputs. First, first term is A complement B complement to C complement. Second is A complement B complement C. Third one is A complement B C complement. Fourth one is A complement B C. Fifth one is A B complement into C complement. Sixth one is A into B complement into C. Sixth one is A B C complement. Seventh one is A B C. Let's consider logic functions. F1 is equal to M0, M3, M4, M6, and F2 is equal to M1, M2, M4, M7. So here are the terms Y0 to Y7, and let's consider F1. F1 is M0, M3, M4, and M6. F2 is M1, M2, M4, and M7. We pass it through OR gate and we get the logical functions. In the same way, we can use PAL in decoders. Next application is state machines. State machines concept used in designing computer program or digital logics. State machine is any device storing status of something at given time. State machine reads set of inputs and changes to different state based on those inputs. Vending machine, subway entrance turnstile are the some examples of state machines. We can see here the sample diagram of a state machine. It receives inputs and it passes through combinational logic and stores it to memory, and we get the output through memory. This combinational logic required for state machine can be can be done using PAL. The state machine realized using programmable logic devices will require lesser number of chips. In some application, the output sequence of state machine need modifications. This can be achieved by changing the program of programmable logic devices. We can use PROM, PAL or PLA. Based on those changes, we get a different sequence of output. Thank you for watching the video. I hope you understood the concept of PAL. So please like the video, share it to your friends, and don't forget to subscribe. Thank you.